First, we must correct the taxonomy. Vitamin D is not a vitamin. It is a secosteroid hormone. It shares a chemical backbone with testosterone, estrogen, and cortisol. Because it is a hormone, it regulates the expression of over 200 genes in the human body. However, on the shelf, it appears in two distinct forms: ergocalciferol, vitamin D2, and cholecalciferol, vitamin D3. While often marketed as interchangeable, the data proves they follow drastically different metabolic pathways. The difference begins at the source. Vitamin D2 is plant-based. It is synthesized by irradiating ergosterol found in yeast and fungi. It is an evolutionary adaptation for mushrooms, not mammals. Vitamin D3 is animal-based. Commercially, it is extracted from the lanolin, grease, in sheep's wool. Biologically, it is the exact same molecule your skin synthesizes when 7-dehydrocholesterol reacts with UVB radiation. Because D3 is the endogenous form produced by humans, our transport proteins, specifically the vitamin D binding protein, DBP, have a significantly higher affinity for it. Neither D2 nor D3 is biologically active upon ingestion. They must travel to the liver to undergo hydroxylation. An enzyme called 25-hydroxylase converts them into calcifediol, 25-hydroxyvitamin D. This is the marker doctors test in your blood. Here lies the bioavailability gap. Clinical meta-analyses consistently show that D3 is approximately 87% more potent at raising blood serum levels of calcifediol than D2. Furthermore, D2 has a shorter half-life and a higher rate of clearance from the bloodstream. It is metabolized and excreted faster than the body can utilize it, making it a statistically inferior choice for correcting deficiency. A critical variable often missing from the data is magnesium. The enzymes required to convert vitamin D into its active form, calcitriol, in the kidneys, are magnesium dependent. If magnesium levels are insufficient, which is common in modern populations, vitamin D remains stored and inactive. High-dose vitamin D supplementation without adequate magnesium can actually deplete the body's magnesium reserves as it attempts to process the hormone, leading to calcification of soft tissues rather than bone mineralization. Because vitamin D is fat-soluble, it accumulates in adipose tissue. This accumulation presents a risk of toxicity, hypercalcemia, though the threshold is incredibly high. The body has a natural feedback loop to destroy excess D3 produced by the sun, but it has no off switch for oral ingestion. However, the toxicity data suggests that D2 is more likely to result in adverse outcomes due to the unique metabolites formed during its breakdown, whereas D3 mimics the natural equilibrium. If the goal is to mimic human physiology, cholecalciferol, D3, combined with magnesium is the biological standard. Ergocalciferol, D2, is a pharmacological analog that, while functional, operates with lower efficiency and stability.